And then, yeah, okay. So today we will continue with the last week. Last week we talked about the introduction of computer-aided geometric design. What is it about this course, right? And we have talked about the Hermite curve. That is a curve that you may be familiar with. If you want to draw a curve in Illustrator or in Photoshop, right? You may have been familiar with it, right? And the next one is the Bezier curve that is famous and very important in computer-aided design or CAD, right? The name of this curve is named from the French mathematician, right, who was working in the Citroën car company, right? And you may read the history of Bezier curve or the Bezier, who is a mathematician, is a CAGD book by Farin, right? I'm not going to tell you into detail about his history, okay? And so I will go to the definition of the Bezier curve, right? Bezier is, as I just told you, he is a mathematician. He is a French guy, and actually he was working in a French company called Citroën, but he was in that company before 1959 or 60 something, right? By that time he developed curve and the surface, right? But he didn't name it as his name until 1972, right? He was a PhD candidate in a university, and then he published his curve, right? That is quite new by that time, right? So that's why the name of the Bezier curve was named as his name, right? I would say that, as I told you, he developed this curve maybe 10 or more than 10 years before, but it was written in French. The thing is that the world knows his name or this curve by his thesis, PhD thesis, and it was written in English. So that is the name of the Bezier curve. And I'm going to tell you another algorithm and another way of representing this curve, but the name is another French guy. That's I'm going to tell you later. But now I would like to introduce you Bezier curve first. If you could remember, last week I've taught you about the convex combination. The reason why I taught you about the convex combination, because Bezier curve will be written in the form of the linear combination as well. Okay, maybe in order to make it easy, I have to connect. Sorry, maybe I have to turn off. Recording. Okay, now can you hear me?
Yes, Ajahn.
Okay, I've just turned on my iPad so I can write something on the screen as well. So I've just told you that we have talked about the convex combination last week. What is convex combination? Convex combination can be written in the form of sigma alpha I pi, when pi is a control point, is a point, can be referred to as a point I from 0 to n, right? So if I would like to define a Bezier curve, I use like this in order to make it French. So suppose I have n plus 1 points and I want to define it, namely P0, P1, P2 to Pn, right? They are the points in Euclidean space of the dimension 3, 3D Euclidean space. Okay, so a Bezier curve can be defined a Bezier curve of degree n. Degree n means the maximum number of the degree is n, and the number of control points or the points that is an order will be equal to n plus 1 points. So we can define a Bezier curve as BNT, right? BNT can be defined in terms of convex combination. P0 and this one, and P0 and this one. P0 can be referred to as the point. Okay, the point we will call it control point. I will tell you why I will call it control point. The points will control the shape of the curve. Controls shape of the curve. That's why we call control point. Okay, and we will have to define in terms of the convex combination, the product of alpha I pi, right? And this one can be referred to as the alpha I, alpha 0, alpha 1, alpha 2 to alpha n. Okay, so here it is a kind of the convex combination in terms of Bernstein polynomial BNIT, right? Multiplied by pi, I from 0 to n. So it is also there are n plus 1 control points where BNIT, I've just said that it is a Bernstein polynomial. Bernstein polynomial is a Russian mathematician. If you could remember about what we call, okay, I will tell you about the formula of the Bernstein polynomial first. Okay, Bernstein polynomial can be defined in terms of n choose I, and then multiply by t raised to the power I, multiply by 1 minus t raised to the power n minus I. Okay, where n choose I is a binomial coefficient. If you could remember, binomial coefficient is the coefficients that we use in the polynomial, right? Okay, and it can be defined as n choose I can be defined as n fact divided by I fact, n minus I fact, and t raised to the power I and 1 minus t n raised to the power n minus I. Okay, maybe I will have to recall you about the Bernstein polynomial and binomial coefficient. If you could remember, if I define a plus b raised to the power or square, raised to the power 2, right? I can write it in terms of a square plus 2ab plus b square. Am I right? And if you want to find a plus b raised to the power 3, you can write it as a square, a raised to the power 3 plus 3a square b plus 3 again a b square plus b raised to the power 3, right? Follow this, you can see 1, 2, 1. They can be called coefficients. They can be called coefficients. So similarly to this one, this the degree 3, right? This is this one. And if you could remember Pascal triangle, you can like this 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, right? This is 1, 2, 1, 1, 2, 1, 1, 3, 3, 1, 1, 3, 3, 1. This is what we call binomial coefficient. And it can be written in terms of ni, or ni is n fact divided by I fact, n minus I fact. Can you remember? Okay.
Yes, I can remember, John.
Okay, thank you. Okay, so I will not recall you again, okay? And then, okay, instead of the place a plus b raised to the power 2, right? If I replace it, I replace a by 1 minus t and replace b by t. Ooh. Okay, a plus b square. I replace it to, I replace a by 1 minus t and plus t, right? Raised to the power 2. Do you remember 1 minus t plus t is equal to 1. 1 raised to the power 2 will be 1. Okay. So if you think t is equal to like b and 1 minus t is a, so they are similar, right? This is a form of the Bernstein polynomials. Bonsai polynomial. Okay, so in order to make it clear, this one is a general form of Bezier curve of degree n. This is a general form. So I would like to give you the more specific form, right? That is the Bezier of degree 3, right? So we will start with the cubic. Cubic means 3. Cubic is a Bezier curve of degree 3. So it is degree 3. So it is there are 4 points, 4 control points, or we can call the order of this curve is 4. So if you could see in this figure, so I define P0, P1, P2, P3. There are 4 control points for this cubic Bezier curve. 4 control points, P0, P1, P2, and P3. And the concept of the Bezier curve, right? It will pass through the first and the last endpoint. In this case, the first endpoint is P0 and the last endpoint is P3. And 3 is the 3 is a degree of this curve, right? And you can see that this curve is drawn in pink, right? This is the Bezier curve, cubic Bezier curve, right? And I would say that the reason why we call these 4 points are control points. It means that the 3 points surrounding by this curve will control the shape of the curve. control the shape of the curve. Once again, that's why we call control points. In this way, once we define or 3 points or 4 points are given, we can come up with a Bezier curve, only one Bezier curve. How can we derive this one? Okay, first of all, we have to substitute the cubic Bezier curve into the general form. As I told you, for the big cubic Bezier curve, we have to concern about 4 control points. If we have 4 control points, we will have 4 terms for calculation. So we have to start from I from 0 to 3, right? And then we can have P0, B0, P1, B1, P2, B2, and P3, B3, right? So the next thing that we have to do is we have to derive the Bernstein polynomial. Bernstein polynomial. Right? First, we have to define here B30. So the formula is 30. T raised to the power 0, 1 minus t raised to the power 3 minus 0. So you can come up with this 1 minus t raised to the power 3. This is the first polynomial. Okay, the next B31t, right? Substitute n by 3, substitute I by 1, and then t raised to the power I, 3t raised to the power 1, and 1 minus t, 3 minus 1. So it yields 3t, 1 minus t squared. Okay, and we can do the same thing, right? We can, if you could remember Pascal triangle one like this, right? So in order to make it easy, we just simply use the coefficient in Pascal triangle. Here, 1, 3, 3, 1, 1, 3, 3, 1. And then you start with 1 minus 3, 1 minus t, 3, and 1 minus t, 2, 1 minus t, 1. And this one is 1 minus t, 0. That is 1. Okay, that is 1. So, and then for term t, this is t raised to the power 0, t raised to the power 1, t squared, t raised to the power 3. So we can come up with the 4 Bernstein polynomial. 1, 2, 3, 4. But once again, if you could not remember, t from 0 to 1. So what we have to check for the next property. Okay, I will. So, okay, here we go to the next one, the next slide. So for the cubic Bezier curve, right, it can be written again in the terms of convex combination or not, right? We have to prove that cubic Bezier curve is a convex combination or not. So first of all, it has to be proven for the linear combination. It is pretty easy. It is obvious, right? Because it is in the form of the sum of product, right? Product of this term plus product plus product plus product. So it can be written in terms of the term of sum of product. So it is summation of Pi and Bernstein polynomial. This is raised to the power 3, and I from 0 to 3. So it is obvious that this is the linear combination. But for the next property that has to be proven, you have to check whether it is the affine combination or not, right? So you have to sum them up. Sum this term, this term, this term, this term. This term are Bernstein polynomial. You have to sum them up and check whether it is 1 or not. So what you have to do is you have to expand this polynomial, right? 1 minus t raised to the power 3, you can expand into like this, right? And this term, you can expand to this, and also this term and this term. So you can see that there are some duplicate terms, right, in terms of positive and negative things. For example, we are considering t raised to the power 3, and we have minus 3 t raised to the power 3. And also we have, so we can eliminate them. And this one we can also eliminate. Minus t plus t, and 6 minus 6 and plus t plus 3. So there is only one term left, that is 1. So the summation of the Bernstein polynomial is sum to 1. So it is affine combination. So it's checked. Check. And the last term, and the last one, you have to check for each Bernstein polynomial whether it is greater than or equal to 0 or not. Whether it is greater than or equal to 0. If it's true, so it is convex combination. So in order to prove this, you can come back to the previous slide. Okay. Once again, I have told you that t is from 0 to 1. T is from 0 to 1, right? If t is from 0 to 1, what is the values? What are the possible values of 1 minus t raised to the power 3? Can you answer me? If t from 0 to 1. 1 minus 0 is 1. 1 minus 1 is 0, right? 0 raised to the power 3 is 0. So 0 is raised to the power, and 1 raised to the power 3 is also 1. So can I write this? So it is 1 minus t greater than or equal to 0. Do you get the point? Okay, it is greater than for sure. It's positive for sure. So next we will have to check for 3t 1 minus t square. I will say that anything that is square, so it is positive. And t from 0 to 1 is also positive. 3 multiplied by positive and multiplied by positive is also positive. So it's positive. Similarly to this case, and also this case is greater than or equal to 0. So I can prove that cubic Bezier curve is a convex combination. Okay, so we can prove that therefore a cubic Bezier curve is a convex combination. The reason why I will have to prove this property, because if you have a set of control points like this, so I will say that if I'm trying to draw a Bezier curve of this control point, the Bezier curve will be like this. The context here means Bezier curve, this is a green one, is if it is in terms of, if it is divided in terms of a convex combination, we can say that Bezier curve will lie inside this convex of these 4 points. When I draw here, this called convex of 1, 2, 3, 4 points here. So using this property, we can guarantee that a Bezier curve will lie inside the convex hull. Convex hull. If we have a polynomial like this, oh no, not the polynomial, the polygon like this, so here is a convex hull of this polynomial, of this polygon, sorry. What we are trying to say is that we can say like this, the control points can form the polygon. Okay, so this is just one representation of Bezier curve, right? We can start with one. The first one, we can represent Bezier curve in terms of the Bernstein polynomial. Second one, I've just told you that in order to show the Bezier curve right onto the screen or the computer, you may have to represent it in terms of the matrix form, as I told you last time, right, for the Hermite curve. So similarly to this case, right, for the cubic Bezier curve, we can also convert it into the form of GMT. Yeah, you may be familiar with GMT, right? T stands for T, let's put up T3, T2, T1, and T0, right? And G, for the previous class, right, for Hermite curve, you have P1 and P4, right? R1 and R4, right? Represent the first and the last endpoint and the tangent vector of the first and the last endpoint. But for Bezier curve, right, we are not going to do with the tangent vector. We will deal with the only control point, P0, P1, P2, and P3. Okay, and then if we want to come up with the metric form or metric representation of a cubic Bezier curve, we can just, that's very easy, right? So we can just only consider the coefficient here, the coefficients here. This is -1, 3, -3, 1. So you can put -1, 3, -3, 1 here, right, according to P0. And then 3, -6, 3, 0, 3, -6, 3, 0, -3, 3, 0, 0, -3, 3, 0, 0, and this is 1 for this one. And the remainders are 0. So this is the way that we try to convert from the polynomial representation into the matrix representation of a cubic Bezier curve. Okay, so now I will conclude a bit about the Bezier curve, right, by showing you the property of Bezier curve. The Bezier curve passes through 2 endpoints. If P0 and P3 are the start and the last endpoint, the first and the last endpoint of the Bezier curve, so Bezier curve we have to pass through P0 and P3. Okay, and if you have B, T, which is the Bezier curve, when you substitute T by 0, you can get P0. And when you substitute t by 1, you can get Pn. Or in this case, for the curve, cubic curve, you can get P3. Okay. So this is the first property of Bezier curve. It has to pass through or interpolate to endpoints. Interpolate means connect, right? Connect to endpoints. And the next property of Bezier curve is affine combination. We have already proved about the affine combination. It is sum to 1. In order to make sure that it can sum to 1, I will have to show you like this. For example, for cubic Bezier curve, I can write it in terms of 1 minus t plus t raised to the power 3, right? But inside this one, it is 1. So it is equal to 1 raised to the power 3. So it will be equal to 1. So in the same way, you can write 1 minus t plus t raised to the power n. So you can come up with 1 raised to the power n, which is equal to 1. So no matter n or the degree of Bezier curve, the summation of the Bernstein polynomial will be 1. Always 1. Bernstein polynomial. Okay, I always like this term many times because you are new to the name of Bernstein polynomial. So I will try to maybe write down it in order to make sure that you will remember Bernstein polynomial. Okay, any questions up to now? And once again, t will be ranging from 0 to 1. Okay, next I will go to the third property, that is the most important properties for Bezier curve, because you want to prove that the Bezier curve should lie inside the Hello, can you hear me? Can you hear me? Okay. Why Aisha cannot hear me? Aisha, can you hear me? The other students can hear you. Can hear me. Okay, I will continue. Okay, we come to the third property of Bezier curve, right? That I just told you that it is the most important property, right? Because we want to check, we want to make sure that the Bezier curve should lie inside the convex hull of the control point, right? The convex combination here, if you can prove that the curve can be written in terms of the convex combination, the curve will lie inside the convex hull of the control point. Okay, this one you have to put the star on it. Okay, 3 star. Okay, lie inside the convex. Yes. What's happened? I don't know, Aisha. Yes, microphone is mute, but I have 2 accounts. If you can see that my other account's microphone is on. What's happened? Hello, hello. Can you hear me? I am speaking. Hello, hello. Can you hear me? 1, 2, 3, 4. Your friends can hear me. Maybe you turn off your speaker. Have to check your speaker. Okay, so back to the lesson, right? This is a convex hull. I will show you in the yellow one. The convex hull will include the boundary that connect each pairs of endpoints. The yellow one is called convex hull. This property will guarantee that the Bezier curve will lie inside the convex hull and will control the shape of the curve. Will control the shape of the curve. Okay, come back to the question, right? Your friend asked me that what does it mean by convex hull, right? Convex hull. This name, you can see this name in the class data structure, but I'm not sure whether your instructors or your teacher would taught you or not. But this one will be in the part of geometric data structure, right? And what does it mean by convex hull? Convex hull means like this: if you have triangle, the convex hull of triangle will be every point that is inside this triangle, including the boundary of the triangle. Okay, this, and also if you have pentagon, okay, the convex hull of the pentagon will be every point here and including the boundary of the polygon as well. These two kinds of polygon we call convex polygon, but we also have non-convex polygon in this term. Convex polygon means open polygon. Open polygon means there is some like this, some space inside the polygon. So if you want to find the convex hull of this polygon, you have to include, oh, what? Right. If you want to find the convex polygon or convex hull of this polygon, you have to include the space as well. Convex hull will cover all of the possible points inside the polygon. This is why we call convex hull. HULL, hull. Okay, it's clear? Okay.
Yes,
So
Ajahn.
I will go to, okay, then this is the next topic, that is the name that I've just told you. This is also the French mathematician. This one was, okay, De Cassejo. De Cassejo is a French mathematician. French mathematician. And his work for oh sorry, the Castle work for Citron company. This is also the French car company, and for the Bezier, he worked for the Renault. It's also the French company. Just okay, and they are all French. Once they invented his Bezier curve, his curves, right? But their report was written in French, but Bezier curve, Bezier, right? Write his report in 1972 in his PhD report. So it was publicized. So that's why this curve named that from Bezier. Even the Castle invented the curve in 1959. Okay, so before we go to the Castle algorithm, so I will stop for a while, and then after a short break, we will try to write a program for drawing Bezier curve. Okay, so we will have a short break for 5 minutes, and then we'll come back.